Okay, perhaps we can start. Welcome everyone and good morning to this, what I think is going to be a terrific seminar on the Australian-German Climate and Energy College on safeguarding biodiversity and carbon dioxide removal approaches. My name's Peter Christoph. I've had a long association with the college and I'm at Melbourne University teaching climate, politics and policy. Just by way of a quick couple of words of introduction, I'll be sharing this session. I just want to very quickly introduce the topic, the speakers, and then just make a couple of quick observations about how we'll go through this seminar over the next hour. I don't think it's important or necessary for me to, well, it's important, but not necessary for me to say a great deal about the importance of the topic. We're all painfully aware of the sort of crises that we face in terms of biodiversity and extinction, to which climate change is a powerful and amplifying feature. One of the paradoxes, I think, one of the problems that we're facing at the moment is that as we work so hard to deal with, to counter global warming and its impacts on the living world, some of the technologies and approaches that we may be developing, paradoxically, may actually have amplifying negative impacts on precisely the sorts of things that we're trying to save in the living world, the species and ecosystems towards which all of our efforts are being directed. So I think it's exceptionally important that we have the focus that this paper is going to deliver, and I hope that all of you will actually get a chance to have a look at the underlying publication to which speakers are going to address themselves, which has just come out in Global Policy on carbon dioxide removal and biodiversity, a threat identification framework. The importance of this paper and the work that our three contributors have been doing enables us to think much more systematically and analytically about the policy approaches and the implications of policies that are being used, which on the one hand are intended to improve biodiversity, the situation of biodiversity, and to remove threats, and yet obviously can work in precisely the opposite direction. Let me introduce all three speakers almost at the same time. I've had the pleasure of being associated with them in a very minor way over the last few years, contributing to each of their doctorates. Each doctorate has covered a very specific and powerful area of concern in terms of geoengineering, carbon dioxide removal, the sort of policies that we're developing to try and deal with the impacts of climate change. So let me just quickly introduce each of the speakers. Firstly, Kate Dooley. Kate is currently a research fellow at the Climate and Energy College. She's got a long association with climate negotiations, has been following the climate negotiations and involved in campaigning around forests and land use and climate mitigation for at least the last 10 years, I think at least since 2009. Kate's a research fellow at the Climate and Energy College, and her thesis was on the issue of land-based carbon dioxide removal and its impacts on biodiversity. Harrould-Kolieb did a terrific thesis on ocean acidification. She's also a research fellow at the Climate and Energy College and a future postdoctoral research fellow at the TransClim project in the University of East Finland. Her work, the PhD, was on international governance of ocean acidification, and she's also continued to work in this area as a marine scientist, as a member of the Rationale Advisors Consulting Group, and also and I think still or formally a marine scientist for Oceana, which is a major campaigning group in terms of ocean impacts. And lastly, we've got Anita Talberg. Anita also did a PhD on climate governance, on geoengineering and climate governance at the university. She's also got a master's in climate change and an engineering degree from the ANU. Anita was formerly the director of the Climate and Energy College, is now Director of Workforce Development at the Clean Energy Council, and prior to all of that worked at the Australian Parliamentary Library, providing research and analysis to members and senators in the Australian Parliament. So each of the three speakers and contributors have worked on this terrific paper. Strongly recommend that you have a look at the paper on threat identification frameworks, and they're going to be speaking. I think the order is going to be Ellie first, and then we'll see how this plays out. Half an hour a half-an-hour presentation, and then I'll just simply open up the floor, the virtual floor, for discussion. So, Ellie, over to you.
Thank you. Good morning, everybody. Thank you for joining us. And thank you to Peter for that introduction. Before I start, I just want to take a moment to acknowledge the traditional owners of the land from which I'm presenting and of the land on which the college sits, both the Boonwurrung and Wurundjeri peoples of the Eastern Kulin Nation, and pay my respects to their elders, past, present and emerging. So as Peter mentioned, this seminar that Kate, Anita and I are giving is based on a paper that we published early in the year. A paper which grew out of several conversations that we'd had concerning the wide and often unaccounted for impacts of geoengineering broadly and carbon dioxide removal more specifically. So as I'm sure you're all aware, that due to our continued delays in reducing emissions, projected mitigation scenarios that limit warming to well below 2 degrees and closer to 1.5 as required by the Paris Agreement rely on large-scale carbon dioxide removal. However, these scenarios haven't given due consideration to the consequences that these interventions pose to biodiversity. Indeed, the IPCC has noted that there is a lacuna in understandings of the impacts of CDR on ecosystems and land degradation. Assessments of CDR techniques most commonly include cost and potential, while frameworks for assessing limitation and impacts are lacking. Moreover, debates around the development of these technologies have historically concentrated on the dichotomy between the need to expand the knowledge base of all options related to emerging technologies and the concern that research represents a slippery slope to deployment. Further, there are conflicting findings in the literature on the environmental and social impacts of CDR interventions, with some suggesting positive outcomes for all, while others, such as the Intergovernmental Panel on Biodiversity and Ecosystem Services, take a more conservative approach, suggesting that all proposed CDR methods included in the IPCC's 5th assessment report will have negative impacts on biodiversity. So given this gap in assessment tools and the conflicting findings within the literature, we constructed a threat identification framework that can assist in the decision-making around the research and deployment of various CDR techniques. Now, before I hand over to Kate to talk about which CDR techniques we examined and the methodology that we used to do so, I want to talk briefly about biodiversity and why it should be a critical element in the decision-making around CDR. So what is biodiversity and why do we or should we care about it? So the Convention on Biological Diversity defines biodiversity as the variability among living organisms from all sources, including terrestrial, marine and other aquatic ecosystems, and the ecological complexes of which they are part. This includes diversity within species, between species, and of ecosystem. So as summarised so succinctly in The Guardian recently, biodiversity is essentially the variety of life in all its forms and all its interactions. Biodiversity is arguably the most complex feature of our planet and it's most vital. Biodiversity underpins ecosystem function and thus the provisioning of all goods and services that are essential for human health and well-being. These ecosystem services can be grouped into 4 overarching categories. The first are provisioning services, which are the goods produced or provided by ecosystems, such as fresh water, food, and oxygen. The second are regulating services, which are the benefits we get from functioning of ecosystem processes, including pollination, water purification, and climate regulation. The third are cultural services, which are the non-material benefits we gain from the mere existence of ecosystems, including recreation, spiritual connection, and cultural heritage. And the fourth are the supporting services, which are the ecosystem services that underpin all other ecosystem services. These are the processes that allow Earth to sustain life and include the water cycle, photosynthesis, and habitat formation. And biodiversity is the basis of all of these ecosystem services. However, biodiversity is currently being lost at such a rate that we are seeing the degradation and cessation of many of these services. The extinction rate is now thought to be 1,000 times the natural rate, and the biodiversity crisis is pushing us close to ecological collapse. Thus, the idea of utilising CDR techniques to combat the climate crisis by further damaging biodiversity and our life support systems is essentially a process of problem shifting with perverse outcomes. Biodiversity should not be seen as acceptable collateral damage in the fight against climate change. Moreover, these two crises are not independent, but are inextricably linked. As climate change worsens, many more species will be pushed beyond their capacities to adapt, resulting in an acceleration of extinction rates and further degradation of ecosystems, which will lower their ability to sequester carbon dioxide and even result in carbon dioxide releases, thereby further exacerbating climate change. Thus, climate change and biodiversity loss are mutually reinforcing crises, and the deployment of CDR techniques that negatively impact biodiversity could ultimately result in an exacerbation of climate change. However, reversing the trajectory of either of these crises will assist in combating the other. Healthy, functionally robust ecosystems will sequester carbon over the long term, contributing to climate change mitigation. And at the same time, decreasing climate change will lessen one of the main drivers of biodiversity loss, thereby enhancing ecosystem health and resilience and contributing to the adaptive capacity of socio-ecological systems. While climate change is becoming the main driver of biodiversity loss, is not the only one, and removing or lessening these other drivers will decrease the rate of loss and benefit both crises. Therefore, any CDR interventions that can help to minimise the negative impacts on biodiversity or even strengthen and restore it should be prioritised. And this is ultimately what we hope to convey through our threat identification framework. I'm going to hand over to Kate now, who will discuss the drivers of biodiversity loss in more detail and outline how we use them in our framework for assessing the impacts of CDR techniques on biodiversity.
Thanks a lot, Ellie, and thanks, Peter. So for this threat identification framework, we based our assessment on the direct drivers of biodiversity loss. Based on the IPBES report, these are in order of greatest impact: land use and sea use change, resource extraction, pollution, invasive and alien species, and climate change. So we identified these and the key sort of characteristics of these. All 5 direct drivers show steady increases over the past 5 decades globally. However, it's also important to understand that these drivers are the result of underlying causes, the indirect drivers of change. So to quote the IPBES report, these are underpinned by societal values and behaviours that include production and consumption patterns, human population dynamics and trends, trade, technological innovations, and local through global governance. So it's the broad demographic, economic, and technological trends that ultimately drive biodiversity loss. But identifying how different CDR options would impact on those broad trends would be very difficult, and certainly at a global level impossible. That would have to be a very specific analysis. So for this paper, we focused on the contribution of carbon dioxide removal options to the direct drivers of biodiversity loss. We thought this was a method that would be useful for identifying low threat or even positive mitigation options for biodiversity, and also those mitigation options that pose higher threats that should be perhaps reconsidered. As Ali said, any climate change strategy that further drives biodiversity loss is a perverse outcome. So the next slide. So we had the 5 direct drivers of biodiversity loss, and then we categorized CDR into these 4 process-based categories. So our aim here was to provide a specific assessment of the impact of CDR on those direct drivers to biodiversity, not any kind of broad assessment of the range of CDR limitations and potentials. So we thought that to do this, it would be useful to understand the processes that different CDR options rely on. So we've identified land use change, regenerative, marine, and chemical as a way of distinguishing these. And then you can see on the slide here the list of different CDR activities that we assessed. So it's not that there's more different, you can get more and more specific in how you identify and assess different CDR options, but we felt this was a good combination or balance of reasonably detailed, but general enough that we could assess the literature to understand these. So, and that it would provide a policy relevant evaluation framework to identify the impacts of proposed CDR options on biodiversity. So the way we brought these together is, or the methodology we used to assess the CDR options was a literature survey of each separate activity. So at the level of BECCS, ocean fertilization, direct air capture, etc. We did a literature survey for each of those activities to identify the impacts of those on the 5 biodiversity drivers. We've then ranked these impacts as positive, negative, dependent on implementation, or no impact. So just briefly to explain what the figure is conveying, red is a negative impact, blue is a positive impact, and then if it's red and blue, that means it's dependent on governance or implementation as to what the impact would be. And I think we have one grey circle where no impact at all. There's no impact on that driver. So the icons are the drivers to biodiversity loss, which I showed on the previous slide. The tractor, bulldozer, is land use change. It's actually so small on my screen, I can't see what the next one is. Oh, then it's like an excavator. That's resource extraction. The temperature symbol obviously is climate change. And the factory is pollution, and the little bug is invasive species. So next slide. So the rest of the presentation, we're going to go through each of these 4 CDR categories: land use change, regenerative, marine, and chemical, and just describe in a little bit more detail where we identified negative or positive impacts on biodiversity drivers. So for land use change, obviously already land use change itself is the leading driver of biodiversity loss. So any CDR options that are relying on land use change are by default going to be high threat to biodiversity. In terms of afforestation specifically, often this is done with exotic, or sort of inevitably this is done with exotic species, because the definition of afforestation is putting forests where forests don't normally grow. So there you already have invasive species, another driver to biodiversity loss. And these exotic fast-growing species often need increased requirements for water and nutrients, which increases runoff and pollution, so further driving biodiversity loss in terms of resource extraction and pollution. Reforestation is much more dependent on implementation. So reforestation can be done with mixed native species in appropriate locations, and then you would remove those problems of resource extraction. There'd be less or no requirements for water and nutrients, and you're not introducing invasive species. For both of these options, however, the climate benefits can be quite uncertain, partly due to reversal in terms of if forests die or burn, then we lose the climate benefits. So this is one of the issues with land use sequestration for climate change. But also often when afforestation or reforestation is proposed or carried out as a CDR or climate mitigation activity, it's done via commercial plantations, which are subsequently cut down and regrown. And the actual carbon removal benefits of commercial plantations are very, very, very small compared to a forest that is left to grow and stand. So climate impacts can be very small, or climate benefits. Just briefly going through the others. Biochar, again, the impacts will be negative if it's dependent on land use change to grow feedstocks. Resource extraction at a small scale, biochar can result in reduced requirements for water and nutrient inputs for agricultural productivity, so it can be beneficial there. But if very large scale biochar exercise would require large scale feedstock growth, that would outweigh the productivity benefits. Biochar application can also make soils less prone to erosion, degradation and contamination, so reducing pollution. For BECCS, the projected land use change in climate models is very large, up to 1,200 million hectares, or for new energy crops in some models. The fertiliser and water inputs for such a scale of bioenergy crops would exceed planetary boundaries for nitrogen use and compete for fresh water supplies, so impacts on resource extraction and pollution. The climate mitigation benefits of BECCS the reversal isn't an issue, but it relies on the carbon neutrality of bioenergy, which depends on the baseline carbon stocks of the land or the feedstocks used, sorry. So it really depends on bioenergy feedstocks as to whether BECCS is actually beneficial to the climate. Next slide. So then if we look at regenerative options, here we've got mostly blue. These options are overwhelmingly positive in terms of their impacts on biodiversity. And the key difference here is that none of these options rely on land use change. They're all existing in improving the resilience and health of existing land uses. So, and all of them increase ecosystem health and agricultural productivity. The negative impacts are basically the potential reversal. So there's uncertainty in terms of climate mitigation benefits if ecosystems were subsequently lost. But activities like ecosystem restoration, soil carbon sequestration, and agroforestry all increase the resilience of ecosystems and make them less prone to reversal and external stresses. Also, healthy intact ecosystems are more resilient to invasive species. They filter air and water, so reducing pollution. So they're having positive impacts on those direct drivers to biodiversity loss. There is a potential for negative impacts from soil carbon due to resource extraction if nitrogen is used to fix soil carbon, but there are organic methods without needing to use nitrogen. So I will finish up there and pass over to Anita. Sorry. Ellycia.
Thanks, Kate. So under the marine category, we examined 4 types of CDR, these being ocean fertilisation, artificial upwelling, coastal blue carbon, macroalgae. And I think it's worth just pointing out that each of these types of intervention could have been discussed under several other categories, including regenerative and chemical CDR. However, we decided to have a separate category, a marine category, for one primary reason, and that is that the governance of marine spaces tends to happen quite separately from terrestrial governance. And thus, for policy-making processes, it's important that marine CDR be considered as a standalone category. However, we acknowledge that this also establishes somewhat arbitrary divides that can create its own friction within policy-making. And this is seen within policy discussions around blue carbon, which bears a closer similarity to terrestrial CDR approaches than other open ocean CDR techniques. Despite this, debates have raged for many years over its inclusion in existing policy frameworks such as REDD+. This is somewhat ironic given that the tidal wetlands, mangroves and seagrasses have some of the highest potential sequestration rates of any vegetation types. These systems, though, are some of the most degraded globally and are still being lost at very high rates. The loss of these ecosystems is estimated to release 450 million tonnes of carbon dioxide globally each year. And it is estimated that the protection, restoration and creation of coastal wetlands can double the current rate of carbon dioxide removal. And these efforts will benefit biodiversity through the provision of habitats, improvement in water quality, offsetting hypoxia and moderating local acidification. However, as Kate stressed just before, similar to forests, these efforts need to restore and replace with native species and avoid the introduction of non-natives. Macroalgae, which can be considered a subset of blue carbon, we considered it separately, mainly because macroalgae or seaweeds don't have root systems and soils that accumulate carbon in the same way that these other vegetation types do. and therefore sequestration on a large scale requires harvesting, export and storage, or the use of these plants. It has been proposed that harvested macroalgae could be stored in the deep sea. However, aside from the energy that would be required for harvesting and transport, it's unknown what the impacts of this would be on fragile deep sea ecosystems. Furthermore, the cultivation of macroalgae could change local hydrodynamics, increase disease and invasive species, and divert nutrients away from natural food webs. So ocean fertilisation is the other main form of marine CDR that is currently discussed in the literature and main policy fora. And while it's proposed that the process would draw down atmospheric carbon dioxide and lock it away in deep sea sediments, there is little substantiated evidence to suggest that this would work on a large scale over a long period of time. Moreover, there are substantial risks of negative impacts to biodiversity, including the upstream effects from resource extraction and transport of the substances that would be added to the ocean to increase algal blooms. It has been suggested that this process could have a larger carbon footprint than the amount potentially sequestered. And the production of large algal blooms may result in eutrophication, lowering of oxygen levels, and trigger of fluxes of other greenhouse gases with high warming potentials, including methane and nitrous oxide. Eutrophication and hypoxia can lead to large species die-offs, and biological activity may also decline in some areas as nutrient supplies decrease due to their consumption upstream by the artificially enhanced blooms. These blooms may also facilitate the move of invasive species to new areas. Additionally, ocean acidification may be shifted from the upper ocean to the deep ocean, where many species are already living close to their limits. Artificial upwelling is a form of ocean fertilisation where nutrient-rich waters are brought to the surface instead of the surface being fertilised by an additional substance. And so upwelling has the same intention of stimulating phytoplankton blooms and thereby drawing down carbon dioxide. However, these waters which would be upwelled are already carbon rich and therefore may not lead to an additional drawdown from the atmosphere. This process may also require large amounts of energy to uplift the large amounts of water. Although renewables are being researched, they're not yet viable. This process is also likely to exacerbate ocean acidification, which has been documented to occur along natural upwelling sites along the west coast of the US. Artificial upwelling, like other forms of fertilisation, may result in shifts in species composition and therefore alter ecosystem function. So on the whole, of all of the marine CDR techniques that we examined, only blue carbon is largely positive for biodiversity. And I'll hand it over to Anita now, who's going to discuss the chemical CDR techniques that we examined.
Thanks, Ellie. So in the chemical category, we have direct air capture with carbon capture and storage, and then different forms of enhanced weathering or alkalinity enhancement on land, lakes, or the oceans or coasts. So in the direct air capture category, direct air capture, we're basically talking about large machines that capture the carbon as the air flows through those machines. And sometimes that air is fan forced. So we're talking about either adsorption methods, absorption methods, or chemical looping, all of which are different ways of basically defining that sponge, whether it's a solid or a liquid sponge capturing the carbon, and ways to, I guess, gather the carbon off that sponge. So the next stage from that is then the compression and storage underground, which is the CCS component. So I'll talk to that separately. But in terms of direct air capture, the land use change impacts are probably less than BECCS that Kate described, but we're still talking about, as opposed to CCS, where we are usually trying to capture the carbon from a point source, from a coal plant or a processing plant. Here we're talking about atmospheric levels of carbon, which are a lot lower, and therefore you need a lot of these machines. So we are talking about quite a large area of land being used, and if that is considered, if remote land is used for that, then we're talking about access roads. So there are those, I guess, infrastructure and access issues that will cause the land use change. The resource extraction depends on the type of solvent used, and as well whether water is used as one of the means for operating the DACs. The climate change impact here we've put as could go either way, as with the upwelling that Ellie just described. You could use renewable energy to power a lot of these, but they are generally energy intensive. We're talking about heating, cooling, running fans, those sorts of activities. And then the pollution again would depend on the chemical solvents used. And there is some research as well suggesting that areas directly downwind of potential DAC farms would have a low carbon content, which could also have an impact on biodiversity and plants. The carbon capture and storage component of it, which would also apply to the bioenergy BECCS that Kate described. We're talking about the biodiversity impacts of drilling, of wells, pipelines, and also the dust pollution that goes with that, and any risks of that carbon actually leaking. The other two categories, enhanced weathering on land, lakes, or on the oceans. What we're talking about here is essentially dispersion of crushed minerals. Those minerals are generally silicates, olivine, limestone, that sort of thing, to capture the carbon chemically. So land use effects go hand in hand with resource extraction. So this is where there is any mining needed for those minerals. There are some papers talking about using waste stocks, so for example, limestone, which would minimize that. But generally we'd be talking about large areas of mining and then transport. The climate change impacts are largely related to the energy costs of crushing that mineral into a state that can be used for enhanced weathering, so quite fine particles for dispersion. However, there could also be positive climate change impacts through reducing ocean or lake acidity. There would be localized spikes in that alkalinity, which could be problematic for those marine forms or other lake organisms. The other benefit could be from a climate change perspective that where you're applying enhanced weathering to soils, it can increase the albedo or the reflectivity of those soils by making it lighter in colour and therefore reduce that localized warming in those areas. So a bit of, I guess, solar radiation management. And then pollution, well, we can talk about the transport of all of those within all those processes, whether that's ship emissions or road emissions. But generally, I think you can think about enhanced weathering as pollution in its own right. You're really adding something to an environment where it isn't intended to be. Next slide, please, Ellie. Thanks. So I think the benefit of what the three of us did with this paper, and in a sense this paper sort of came together on its own, was really for this final table. And you could use other categories, you could use other activities, you could broaden it to include methane capture rather than just carbon, and you could include other geoengineering methods. Excuse me. But the usefulness is really being able to stand back and look at this table. And we can see clearly, and you would have heard through the discussion, that there are some positive CDR methods in terms of biodiversity impacts. There are negative ones, and there are ones that really depend on the implementation. But what this framework allows you to do is really step back and have that visibility. So clearly, any of those processes that rely on land use change are going to have a negative impact on biodiversity and increase biodiversity loss. So things like afforestation and BECCS, bioenergy and carbon capture and storage. The marine options, with the exception of blue carbon, and a lot of those chemical options were problematic. Excuse me. But there is also the ability through this to have a look a little bit more in detail about what are those implementation changes that could take place to switch it over from being a driver of biodiversity loss towards actually increasing biodiversity benefits. Next slide, please, Ellie. So really, to sum up, the point of this was really to have a look at CDR options. I mean, they present a really, well, all geoengineering methods, but we're looking here at CDR, present strong governance challenges both at the global and the local scale. So being able to assess the drivers of biodiversity loss in this governance framework for us was a way to link those global and local ecosystem consideration. So we see this framework as a way to help identify and eliminate dangerous CDR methods, but also to guide decision-making around research and implementation. So a lot of the literature around the development of these sort of methods and technologies has historically focused on that dichotomy between the need to do more research and expand that knowledge base on all emerging technologies, to this concern that research is this slippery slope to deployment. If we have this sort of framework where we can step back and say, well, there are areas where it really is not beneficial to look any further, but there are areas where research could potentially move us from a more dangerous method into a method that is beneficial to biodiversity and climate change. So we're happy to open it up to questions now. I think there's some already in the Q&A.
Right, thank you. Perhaps the best way to deal with this is to actually have the people who pose the questions ask them directly. Daniel, I think you were first. All right, in the absence of your direct presence, so Daniel Hanish has asked, how is biochar use a negative in relation to exotic species? I would have thought it'd have little impact on the baseline condition.
Yep, so I can answer that one. As I alluded to when I was talking about it, biochar really depends a lot on the scale, and like any bio feedstock dependent intervention, the same for BECCS, it depends on the source of the biomass that you use for the biochar. So you have to burn something to create biochar. If that is new energy crops grown to then burn to create the biochar, that would represent invasive species if it was done in areas that weren't already farmland. And this really comes down a lot, what the literature showed is a lot of the negative impacts here come down to scale. If really large scale is required, then that will be potentially natural grasslands in particular are at the biggest threat of conversion to bioenergy crops for biochar and for BECCS.
Terrific. I've got another question. Paul Burnaby, do you want to ask this directly?
Sure. Yeah, my question is around, I guess, existing planted exotic forests being reforested and that wood used in mass timber construction in the building industry. I'm just curious the impact that has, from a biodiversity, your view on that, but also from a climate change perspective, with sort of locking that wood up. If someone's done some thinking into that.
Yeah, I can take that one again. So I'm just thinking through all the sequence of events you laid out. Existing exotic forests are reforested, and then the timber's used in the building industry. Was that it, or did I miss what kind of species they were?
Yeah, no, that's it in a nutshell.
So the biodiversity impacts then are going to be the same as for any exotic forest. I mean, it's really just a continuation of a commercial plantation, and they actually have really, really negative impacts on biodiversity, commercial exotic species plantations, as well as pollution in terms of water runoff and nutrient requirements. So there's a lot of problems there. Not that I'm advocating that we need no commercial plantations, because we do need timber, but expanding them greatly for climate change mitigation would be a bit foolish. In terms of timber in the building industry, so yeah, that's potentially a really good solution, as well as the CDR potential. There's the I forget what it is, the substitution value of then not using steel or cement, the materials that timber can replace. It's a really difficult, I have actually looked into this a bit in the literature, and it's a really difficult area. There's not a lot of research. in terms of the scale of mitigation of carbon sequestered in that timber, but it does tend to be very small, and it's because it's such a really small portion of what harvested wood products are used for. Majority of harvested wood products, so they are ranked in terms of longevity, short-term and long-lived harvested wood products in terms of accounting for climate mitigation. And even the long-term harvested wood products tend to be long-term in terms of a year or 30 years, but certainly not hundreds of years. And so it's only really in that construction industry that you might get the timber there locked up for hundreds of years, which is what you would require to really count it as a mitigation option. But it's very small scale so far, and it presents big accounting difficulties, and there's not a lot of research on it, I would suggest.
Thanks, Kate. Can I just ask, before we go to the next question, if anyone has questions that they want to ask, can you just submit them using the Q&A component of your screen, so I get a sense of what's coming forward? Look, the next question is from Stephen Todd. Stephen, do you want to ask it directly?
I was actually hoping you would read it for me, but anyway, that's fine. So look, it's a blunt question, because obviously there's a lot of research around Peter Andrews' work in natural sequence farming, and what seems to be misunderstood in Australia is that he's using those pioneer species to slow down the water and increase the hydrological function of the landscape, which then allows indigenous species to recolonize that area. And obviously then you get the biodiversity increases, so it's a win-win, but it's still viewed in Australia as introducing invasive, non-Australian, non-indigenous species. So I was wondering what the overall view on that would be. And I'm not expressing a view there, I'm just asking the question innocently.
Yeah, I'm just looking at that. I don't know if Anita or Ali want to come in on this as well. It's not something I've really heard about or looked into. I can see potentially the benefits of it, but just to say that invasive species do cause a lot of problems that are unintended or unforeseen. And in Australia, we have probably the best examples of invasive species nightmares in the world that were introduced for good purposes originally. So I'm not sure, but it's not something I've looked at specifically.
If I could just interrupt, it'd be well worth having a really good look at what Peter Andrews is doing, because he's been castigated over the past 20, 30 years. I think now people are starting to look at that biodiversity increase and balance that invasive species up with the some benefits in a very simple matrix, where he's planting willows and, dare I say, blackberries around water courses and slowing the water, and then it spreads through the landscape. But then what he actually does, and increases more water coming out of the land than there was actually entering it at the start. It's an incredible thing to look at. But it's called natural sequence farming, because then the indigenous plants then start to recolonize that area, and through that natural sequence, the invasive species then become subordinate to the indigenous species.
Yeah, I'll have a look at it. It sounds interesting, but risky.
Daniel, you've got another question or a comment perhaps that everyone should focus on. Okay, maybe I'll read it out. So it's a comment from Daniel Hanish, who says he can't unmute. These categorisations are based in large part on generalisations. Specific projects could have completely different impacts from what is suggested depending on the particular location or method or risk assessment. So is this communicated in your paper? For example, your ratings of biochar impact in relation to exotic species assumes exotic plantations supply feedstock, whereas the feedstock could come from waste products. So how nuanced can the sort of categorisations, the sort of the approach that you're using be made, or what might be the failings if it's taken at too high a level of generalisation?
I'll take that one. So absolutely agree with that question and that premise, Daniel. So obviously this was to demonstrate the utility of looking at the drivers of biodiversity loss as a way to understand the considerations for some of these CDR methods. But you could look at different categorizations, as I mentioned. You could look at more detailed specific activities within each of those methods and look at each of those categories in line with each of those examples. The other point to make is that this isn't a risk assessment, this is a threat identification. So this is really a question about whether you need to look any further into this area. Really, are there alarm bells from the get-go, and is a risk assessment needed? So we definitely didn't want this table to be sort of a fundamental anything. It was really an example of how you can use this idea to start to understand where it might be worth doing more research or understanding issues a little bit better. Did either of you want to add anything to that, Ellie or Kate?
I'll just quickly add, I think that the point of the paper was actually to be fairly general at this stage and to show the utility of the framework. And so, and we utilized what data or what information is in the literature at the moment. We didn't go out and do, you know, new research. So I think that is actually sort of, yes, it is very general, but it was meant to be general at this stage, and just purely to prove that, or to show that the framework could be utilized. But as Anita said, could be utilized. You could do this with several different categories of blue carbon, for example, and show how each of those different methodologies would have different threats involved. So it was meant to be general at this stage. Yeah.
I mean, interestingly, this suggests this sort of high-level dashboard approach, which I think has got enormous value for identifying threats and consequences. The next step is, of course, application. And without wanting to suggest more work for the three of you, but it would be very interesting to actually take this the next step and see it applied, and to work out how the indices might work. There are obviously potential conflicts or contrasts between different elements of each of the actions. So having a case study approach, taking this the next step, would be a really interesting thing to do. Have you thought about doing that?
It was already hard enough to get the three of us to agree on how we were going to focus this paper so that we could all sort of have some input that was at, I guess, the same level. Each of us feels that we could apply this at different depths or levels of detail in different areas, and ways it would be more useful in some areas than others. But really it was to raise a really important point, which is there's no point looking at these methods if you're not going to be considering things like drivers of biodiversity loss. So that was the first point. And the second point to say, well, this is a really policy relevant, simple framework that we can use to take it to whatever next step you need to, and to eliminate a lot of these ideas that are still being talked about when really shouldn't be anymore. And this is a simple way to say that. But yes, you could absolutely take a case study of any one of these methods and go that way. And we actually sort of hoped that in an area where there was enough literature to do that, it may drive someone to do that.
We've got another question from Stephen. Stephen, do you want to?
Yeah, look, I'm very, very impressed with what I'm seeing from the point of view of your analytical approach to it and the pressing of biodiversity as the key driver in this. So that's why I'm asking the question about kelp farming, which is becoming very fashionable globally. I'm just wondering what the panel's view on using the agricultural activities of the land in the sea. Is that a positive or a negative outcome, particularly if you're drawing down carbon and then reharvesting that kelp and using it for land fertilizer products? From your perspective, is that a potential negative impact on the ocean ecological system? Or is that going to create more pioneer species where you actually want them, particularly if it's grown on hemp rope, so it's a biodegradable rope? You'll probably note that all my questions are heavily loaded.
I'll take that one. With kelp farming, I think that is actually one of the examples where it is really site specific as to whether it's going to be a positive or negative. There are certainly some concerns around the introduction of invasives, changing the hydrological cycles in those areas because of the addition of large kelp farms. So there certainly can be really negative ecosystem impacts from large kelp farming. However, with that said, I think that there are some really interesting positives, as you mentioned, in terms of those harvesting the kelp and using it as feedstock and things like that. So I think actually to use this framework and have break it down by different kelp farming options would be a really interesting next step to see where the positives and negatives fall out. I think there's also some really interesting examples down in Tasmania where they're looking at introducing kelp farming around areas where there are fish farming happening. And so fish farms tend to produce a lot of nutrients, add a lot of additional nutrients into natural ecosystems, which have extremely negative impacts on the ecosystems. And additional kelp farms around those fish farms can actually draw up a lot of those additional nutrients. So co-locating aquaculture and kelp farming can actually be a positive to the ecosystems. So again, I think it's really site dependent, and I couldn't talk globally as to how aquaculture would benefit at this stage, whether it would be a benefit or a negative.
One of the things that the Southern Ocean Carbon Company are actually doing is dropping the hemp ropes in a prospecting manner, and then that allows the indigenous seaweeds to appear, so they're not sort of seeding it and not looking to introduce invasive species. So they're doing it in a really sympathetic way to the ecosystem. So there's really good opportunities at this stage to make sure this is all baselined and discussed in a really open way to see what's the best outcome.
I missed what you said at the beginning. Sorry, my internet connection's a bit patchy. But I think sort of it needs to be done, as you said, in a way that's sympathetic to the natural ecosystem. And whenever, and as Kate mentioned earlier, whenever you're introducing non-Indigenous species, you're always changing the natural ecosystem and at risk of negative impacts. So I think that there always needs to be huge amounts of caution employed when introducing non-natives into a system. But that's not to say that there couldn't be positives in some cases, but I think non-natives always needs to be huge amounts of caution around that.
Well, I suppose that the good news is the Southern Ocean Carbon Company who are working in Tasmania are actually dropping virgin hemp rope into the ocean to see what actually colonizes the rope. So rather than actually introducing species and then trying to fix the problem, they're saying, what's there? How can we make it better? So there's some really good opportunities with yourselves to grab that data and then create a framework for other farmers to say, this is the way it can be done, where it's actually regenerative.
Yeah, and so regenerative is always going to be a better option than introduction.
Right, thank you. We've got time for one more question. I think this is almost a piece of real estate advice to Simon Kerr. Simon, do you want to ask your question?
Thanks, Peter. It's a bit of real estate advice and dragging us down from the high level sort of really interesting discussion we've been having. But we're looking at buying some land to conserve, obviously for ecological purposes, but I'm particularly interested in maximizing this carbon sequestration potential. So any advice really, my thought is we looked at a few well-established forest blocks, but my view is that they're already well established, so therefore they won't really add a lot to carbon sequestration. Therefore, probably should buy some degraded land. Any thoughts?
I could give some thoughts on that, but I'm definitely not any kind of investment advisor. So, but in terms of the carbon sequestration potential, it would depend, I think, on the distinction between if you're looking at this in terms of carbon credits under the Australian Solutions Fund, whatever it's called now, the Carbon Farming Initiative, or if you're looking at actually the real benefits to the climate.
Yeah, real benefits to the climate. I'm not particularly interested in the carbon.
In terms of real benefits to the climate, protecting existing natural intact ecosystems is always the #1 priority. The carbon that can be lost from an existing forest is larger than what you would sequester back into regrowing a forest, and irreversible in some ways, irreversible in terms of biodiversity impacts. As well as existing forests will continue to sequester carbon. So I would say that's the most beneficial, protecting existing intact ecosystems.
Thank you.
Terrific. Look, I think we've come pretty much to the end. Neat, Kate, Ellie, do you want to add anything else? Any other final concluding comments? No pressure.
No, but thanks for all the great questions and attendees. It's been really interesting.
So can I just conclude with a couple, unless Neat, Ellie, anything? Couple of quick concluding comments, if I may. Firstly, for those of you who are interested in reading the paper, and I strongly, strongly urge that you do, it's been published in Global Policy recently. The paper's called Carbon Dioxide Removal and Biodiversity, a Threat Identification Framework, and the link to it is in the chat. Kate's put that up. Secondly, thank you everyone for coming and participating. I think this has been a terrific seminar and an incredibly important one. The more you follow this area, I think the more you realise that this is the sort of approach that is desperately required in terms of some of the decisions that are being made without much attention either to biodiversity impacts or to the ways in which we think about integrating negative emissions, zero net emissions policies in the real world. So thank you everyone for attending the webinar. Thank you especially to Ellie, Kate and Neat for a terrific presentation. I hope everyone has a very good break if you do nothing else between now and the end of the year.
Thanks, Peter. Thanks, everyone.
Peter, thanks a lot.